Today we will have the presentation of Jas Purewal about how would be the operation of engineering center in a Mars habitat. Hello, Jas. You are welcome to start your presentation. Okay, thanks so much for your participation in this Space Analog virtual mission organized by Habitat MARTE.
Thank you, Julio. Okay. Can everyone see my screen?
Yes.
Yes.
Okay. Yes, thank you for the introduction, Julio. This was the presentation I originally gave at Mission 42, and I've adapted it now for Mission 44. So it will be about the engineering facility. Just a quick introduction, going through what the presentation will touch on. So the general responsibilities of the engineering facility. Then we'll talk about some potential construction methods of the actual engineering module itself. And then I've done a possible layout concept, then go into the normal duties, crew requirements, and the main focus of the mission, which is the contribution to food production, followed by the dust storm activities and the recommendations to the rest of the crew and guidelines for daily activities on Earth. So the general responsibilities of the engineering facility will probably be mainly concerned with maintenance and repair of the entire station. And this will include the vehicles, the rovers, the spacesuits, and basically the engineering and technical equipments. And as part of that, it's going to be important that each crew member is capable of carrying out this maintenance on an individual basis. So there will obviously it'll be necessary to give guidance and training so that every crew member is autonomous and independent. With that in mind as well, each facility of the habitat should have its own set of maintenance and repair tools. Also, health and safety of the station will be paramount, and part of that will be the health and safety training for each crew member. In addition to that, obviously we'll be arriving on Mars with many technologies, but the experience of actually living on Mars is going to require the development of new technologies and adaptation to the already existing technologies that we bring with us. And with the main aim to provide a sustainable technological solution. The engineering facility is likely to work very closely with the power station to ensure safe and adequate delivery of the environmental conditions, the life support, and also power to all of the station. And I do believe it also will have some support tools for the scientific research as well. So for example, the rovers that will be required for extravehicular activities are going to be provided by the engineering station and maintained by the engineering facility. So some considerations when building a Mars habitat. The main considerations are going to be protection from the elements, such as the dust storms and also radiation. So that's like the biggest consideration here. But also you have to consider the comfort of the crew, the atmospheric, environmental conditions, the life support, and then things like the cost of construction and material availability, the time to construct, and also how easy it will be to maintain. In terms of protection from radiation, low atomic mass elements are pretty advantageous as they generate less secondary radiation when impacted by particles. So you can see on this table on the right, I've highlighted that water is considered pretty good in terms of radiation shielding. Obviously, water itself is a liquid, so ice would be a much better form of using this. So some potential construction methods. We've talked a bit before, I think, on 3D printed habitats. So I focused a bit more on the sulfur concrete made with Martian soil. The biggest advantage of the sulfur concrete is that it's sustainable and all the materials are available in situ. It's also going to be twice as strong as concrete on Earth. It probably will require solar panels to melt the sulfur, and it can be melted down and recast, and therefore it's reusable. Disadvantage to it is that it's not resistant to high temperatures, so we would need to look at engineering high temperature resistance. And like standard concrete, it's probably going to require some kind of rebar. And the idea would be to maybe send robots to build the concrete structures ahead of human arrival. And then when the humans arrive, they could install an airtight membrane inside the structures. And then, as we mentioned, there's also the idea of 3D printed habitats, which would then be surrounded by ice for radiation protection, or inflatable, such as the Mars Ice Home, which is a concept that I've linked in the at the end of the presentation. There's like the section of resources and references. And then the use of caves and lava tubes as well for Mars construction. And there's no real reason why you couldn't use a combination of all of these. So potentially a 3D printed frame on top of which you could put the sulfur concrete is one possible. So here's a quick example of some of these. So on the left is a picture of a potential lander. It lands on Mars, it inflates a dome, and then the dome is coated with water, which then freezes, and that becomes your permanent habitat. On the right, we have an image of a potential underground structure, but also, as you can see, it's got some windows and glass. So the type of glass that you could potentially use from this, there are various companies that are looking into radiation protection from glass composites, such as a lead acrylic from Mars Shield. So you would need to make sure that the glass obviously provided some radiation protection. So this is my idea of a potential layout concept of the engineering facility. So on the first floor, you can see this is the living area where, for example, as we're discussing now, if you were to be trapped due to a dust storm, there would need to be an area where a crew member could actually live quite comfortably for a week or longer. So you've got the workout area here, and then the storage area. And then there's obviously some rest area as well. If they had to stay overnight, then that would be where the crew member would sleep, and the hygiene facilities as well, where you would obviously, again, for overnight stays, that would be very essential. And then I've just drawn the stairs in the center where you could go down to the ground floor, which is where the work would be carried out. So there would be the repair and maintenance stations and the tool stations. And these would include, I've imagined, 3D printers. There would be the research and an innovation station, and then the communication documents and kind of the office where you might have your computers and other IT equipment as well. The green area surrounding both the first floor and the ground floor is an area set aside for food production. So this could consist of like hydroponic bays. It could be like vertical gardens. And then a modular section to the side would be where you would house and maintain the rovers and drones and other vehicles for extravehicular activities. So the normal daily duties of the engineering facility would be, as mentioned, to maintain the station, the tools, the vehicles, and spacesuits and drones. It would also involve some health and safety checks, risk assessments, and testing all the equipment, making sure everything's in good condition, such as the spacesuits, and also monitoring the best practices and developing new processes. I think engineering facility would also be extremely actively involved in the innovation of new technologies. And in terms of supporting the entire station, they would be supporting, say, the main station, for example, with communication, and the food production with perhaps innovating new technology, vehicle maintenance and medical tools and equipment. Also, I think in terms of the power station, the engineering facility would work very closely with the power station to ensure the delivery of power to all areas of the station. And also provide engineering specific training to the crew members in various other parts of the facility. So the crew requirements. The ideal crew size based on research is between 3 and 6. 6 is actually considered optimal. However, due to food consumption, other resources consumption, and mass considerations, it would be favorable to reduce your crew size down to 3. So reducing your crew from 6 to 3 astronauts actually allows initial mass in low Earth orbit reduction by around 34%. So it has a very important impact on the choice of entry, descent, and landing systems. Ideally, your initial crew could be 3, but then another crew could, and you'd set up your initial habitat, then a second crew arrives, again, maybe consisting of 3 people, and that would be how you then begin to expand the habitat. With each additional mission, new crew members would potentially arrive, by which point you would already have established your initial habitat base and would have a much better infrastructure for supporting a much larger crew. So currently, for example, NASA astronauts on the ISS require 0.86 kilograms of food per meal per day. And water, obviously, is very heavy, so transporting that to Mars is going to be extremely difficult. And the average American uses 130 liters per day. Obviously, that is quite extreme, and crew members traveling or living on a Mars habitat would have to reduce this to less than 50 liters per crew member per day, probably considerably less. So it highlights the need to generate as much food in situ as possible, and also locate water sources on Mars itself and recycle and purify the water sources as well. And the need to grow food as well, like growing plants and algae and mushrooms, and also insects. These can all be grown in artificial environments using artificial light, and then be preserved as well, so that you have a store of food production. Insects in particular would be an excellent source of protein. So the silkworm is one that is being considered currently as a potential food source for astronauts. It's almost entirely protein, and they breed very quickly and obviously consume very little space and resource. So it would be an excellent source of protein to take with you onto Mars. And it would be self-sustaining as well. So in terms of the engineering facilities' contribution to food production, I believe that the engineering facility would be required to basically contribute to things such as the food chamber, perhaps using a collapsible food chamber or modular units for transportation, the environmental controls, so life support, temperature, humidity, all these things would require very much engineering facility hands-on work to maintain and to develop it initially as well. Lighting for the food production, so different wavelengths of light obviously yield better results and also have different power consumption. And the engineering of the bioregenerative systems as well. So as you can see on the right-hand side, this is just an example of how plants can support the bioregenerative life support system. And here on the bottom right is an image of a potential transportation pod for plant growth. So because my idea is to have each facility independently also growing some food, not obviously on the scale of the main food production facility, these smaller pods could be used to transport those plants and other food sources from the main food production facility to the other facilities on the habitat. And obviously, protection from radiation would be a consideration that would need to be engineered. The engineering facility would be responsible for repairs and maintenance, and also, again, innovations based on the Mars experience. And genetic engineering as well. So when considering food production, plants, insects, it could be considerably advantageous to genetically engineer them such that they breed faster and potentially yield more, they produce more and yield more, as opposed to the natural plant itself. And although genetic engineering might be more of a biological kind of topic, it also does require engineering facilities support as well to generate the tools and the things that are required. So in terms of the lighting that I mentioned, it's red and blue light is by far the most energy efficient. And in addition to using artificial blue and red light, there's also the concept here on the right-hand side of using solar collectors for possible plant growth underground. So you would use the solar productions here on top of the ground surface. And as you can see, underground is where the plants are, and that is where the solar collectors would then transport the light for the growth of the plants. So dust storm activities would include developing methods for dust removal from stations, or the entire station, and also solar panels, maybe those solar collectors as well, if those were used. It would be required to ensure that the backup and emergency systems are operating correctly, especially things like life support. This would require liaising with the rest of the crew in other areas to provide engineering support, monitoring the station environmental controls, requesting safety reports from each area of the station, identifying possible risks based on these reports, and maintaining the local food production of the engineering facility, also maintaining the engineering tools, and then possibly adapting the rovers to be deployed during the dust storm to monitor the external conditions. And obviously, the engineering facility would provide reports to the other areas of the station as well, and potentially collect external sensor data and report that to the main station. The recommendations for the rest of the crew would be regular systems checks and maintenance, and then to report on their environmental conditions and life support systems, communicating with the rest of the crew on a regular basis if possible, preparing and sharing daily reports, sharing reports with the main station. I imagine that the main station would coordinate the rest of the facility, and maintain safety procedures and best practices, and to also alert the engineering facility immediately of any engineering issues, and maintain a particularly close eye on power plant operations. So the guidelines for daily lives on Earth would be to maintain routine and schedule, include exercise in your daily routine, also include mental well-being exercises and practices as well, such as creative hobbies, maybe music or meditation. Communicate with others as much as possible, preferably at least once a day. Take on some mental challenges as well, to keep the brain active. Take on a meaningful project, and also in general, just working on your personal development, working on adaptability. And also new Mars technologies could have a significant impact and application on Earth. And that's the end of my presentation. So if I go back, stop sharing.
Okay, Jas. Wonderful presentation. Yes, congratulations.
Thank you.